All right, welcome back, Algebra 1. Today we are continuing talking about exponential functions. We are talking about graphing exponential functions. So we talked about last week how exponential functions, they're these functions that have these curves that like increase exponentially, and it gets faster and faster and faster and faster, and it has a rate that it's always multiplying by, so it's always doubling every time or tripling or cutting in half every time. That's what we looked at a little bit on Thursday, Friday of last week. So today we're going to talk about how do we graph exponential functions. So once again, our formula for an exponential function looks like y equals a times b to the x. Now, a represents our y-intercept in the equation. B represents our scale factor, the amount we're multiplying by, or our rate is another word you're often hear for it. That's the amount we multiply every time. And then x is, of course, our input. Y is, of course, our output. So we want to be able to learn we're going to look at graphing these, and we're going to see if we can notice any patterns from our table to our graph to our sort of some of the features of the function, sort of the key features. So let's start with this one. So we have y equals 4 times 2 raised to the x. Now, starting this table, I could just plug in -2, -1, 0, 1, 2. I could plug in and go piece by piece, but I know that that first number is always going to be my y-intercept. So 4 is going to be my y-intercept in this case. And I know my y-intercept occurs when x is 0. So that means I have 4. And b is my rate of change, which in this case is 2, or my scale factor. That's what I'm multiplying every time. So I'm doubling every time. So if I take 8, or if I take 4 times 2, that gives me 8. Times 2 again, that gives me 16. I can also think about going backwards. What number times 2 gives me 4? Well, 2 times 2 gives me 4. What number, doesn't look like a 2. What number times 2 gives me 2? Well, 1 times 2 gives me 2. So I can also work backwards with this rate. So I don't have to necessarily plug in -2 in for x to get 1, plug in -1 for x to get 2, plug in 0 for x to get 4. I don't want to have to calculate every single point. I can, assuming I know my y-intercept, assuming I know my rate, I should be able to get all my other points. So let's graph this now. So I have at -2, we have a height of 1. So -2 is roughly about here. I know I don't really have a grid. We're going to have a height of 1 about that. At -1, I have a height of 2. At 0, I have a height of 4. At 1, I have a height of 8. And then at 2, I have a height of 16. So this is my function pretty much. It's going to start super low, right along that 0 line, right along the x-axis, and then it's going to increase very rapidly. And my curve's not the best, but it's going to go in each direction. It's going to go up and up and up and up. So this is an example of exponential growth. When our function is increasing or decreasing very rapidly as we're going either really high up or really low towards negative infinity, that's an example of growth. Decay is where our function gets smaller and smaller and smaller and gets closer and closer towards that x-axis, or closer and closer towards that asymptote that we talked a little bit about on Thursday, Friday. So in this case, it's an example of exponential growth because I'm growing very quickly. My y-intercept, I know because it's my a, is 0, 4 is my y-intercept. The asymptote, once again, the asymptote is a word that we use to represent what is that line that our function gets super, super close to but never actually touches. In our case, our function is going to get super, super close to this x-axis but never actually touch the x-axis. I know my picture isn't perfect because my hand drawing isn't the best, but our function never actually is touching this x-axis. It's getting super, super close, but because I can keep going backwards, I can keep dividing by 2 and dividing by 2 and dividing by 2 and dividing by 2. And just like with Jeremiah in our warm-up last week, where he's going to keep getting closer and closer and closer towards the door, but he's never actually going to be able to leave the class because that distance is never actually going to hit 0. We can keep dividing and dividing and dividing, and we can get exponentially close to 0, but we'll never actually touch 0. We'll always have something left over. So our asymptote is going to be our x-axis, which is y equals 0 is our asymptote. That's that line, y equals 0. And then our domain or range of our function. Now, once again, domain represents all of the x values of the function. Range represents all the y values of the function. So we want to figure out what is our domain. So if I think about it, my function can keep going and going and going and going in this direction. It can also keep going and going and going and going in this direction. It might look like my function is going to stop and eventually just go up, but I am technically going to the right every single time. It just is increasing very, very rapidly. So our rate of change that we're going up is super high. So it looks vertical, but I'm still going at a slant technically. It's just very, very rapid. So our domain, we can actually go from anything from negative infinity all the way to positive infinity. So negative infinity, oh, that's a terrible infinity design. Negative infinity is less than x, which is less than positive infinity. All the way from negative infinity to positive infinity, any number is going to work for this function. Another way we talked about writing that earlier in the year was all real numbers was that capital R with that extra line in it. That represents all real numbers. So from negative infinity to positive infinity is our function. Now our range of our function, our range represents the y values. So what's the lowest our function can go? What's the highest our function can go? Well, looking at our function, we know we're going to get super, super close to 0, our x equals 0, our asymptote, but we're never actually going to touch it. And our function is going to keep going up and up and up and up. So our range of our function is going to be everything from 0, but we're never actually going to touch 0. So we're going to be x is greater than 0, but less than infinity. So we're going to get super close. So we're not going to be greater than or equal to because we never actually touch 0, but we're going to get super close. So we're going to be greater than 0. Or we as close as possible, but never actually get there. And this is our function. Let's look at another example. All right, I have y equals 4 parentheses 0.5 raised to the x. So once again, I want to fill in my table. So I know my y-intercept is going to be that a value. So in this case, it's 4. My scale factor, my rate that I'm multiplying by is 0.5. So that means I'm multiplying by 0.5 every time. So 4 times 0.5 is 2. 2 times 0.5 is 1. 4 divided by 0.5, if I think about going backwards, I'm dividing. 4 divided by 0.5 is 8. Divided by 0.5 is 16. So this is my function. So negative 2, 16 is like way up here. Negative 1, 8 is down here. 0, 4. 1, 2. And then 2, 1. And then looking at this pattern, I can see that my function is getting lower and lower and lower and lower and lower as we go. We're cutting in half and half and half. And eventually those halves are getting smaller and smaller and smaller. That it looks like we're hardly changing at all because we're hardly losing anything because we have hardly anything there. So this is an example of exponential decay. We're decreasing and decreasing and decreasing and decreasing. We're getting smaller and smaller and smaller. Our amount is decreasing. So we are decaying. We're losing amounts. Our y-intercept is the same. It's still 0, 4 based off of our a. Our asymptote is actually also going to be the same line. We're getting closer and closer and closer to x equals 0. But once again, we're not actually touching. We're still staying above. Or sorry, not x equals 0, y equals 0. My bad. X equals 0 would be the y-axis. Y equals 0 is the x-axis. Our domain of our function. Now, once again, I can keep going back to the left. I can keep going farther and farther to the right. So my domain can represent all real numbers, once again, from negative infinity all the way to positive infinity. In my range, if I look, I can go all the way up to positive infinity on my left side. And if I keep going towards my right, I'm going down and down and down, but I'm always getting up to that 0. So as long as my x is going to be, or my y is going to be any number that's greater than 0 all the way up to positive infinity. So 0 is less than y. So as long as, and I could technically put greater or less than infinity, but as long as y is greater than 0, we know the top half of it, the highest we can go is up to infinity. What if I have this funky fraction? Funky fraction, that's a good alliterative. All right, g of x equals 8 times 1 over 4x. So once again, filling in my table, thinking about my y-intercept. My y-intercept is going to be 8 because of a. My rate of change is 1/4. So 8 times 1/4 is 2. 2 times 1/4 is 0.5. 8 divided by 1/4 is 32. And I can plug these numbers in. So negative 1 to the 32nd is way off my graph. That's way up here. 0 to the 8th is all the way at the top. 1 to the 2nd, or 1, 2, I don't know why I'm saying to the power. 2.5 is like right here. So this is a super steep line because our rate is 1/4. We're decreasing, we're decaying very rapidly. So once again, we are decaying with this. Our y-intercept is at 0, 8. Our asymptote is once again at y equals 0. We're getting super, super close to that. Our domain, once again, is all real numbers. And our range, once again, is 0 is less than y. Nothing's really changed besides where that y-intercept occurs, but it's still exactly the same. We have our y-intercept, we have our rate, and we can easily fill out that table with this information. Super easy, lemon squeezy. That's not a phrase. All right, what about if we have a negative? For example, y equals negative 8 times 2 to the x. How is this going to change our function? Well, let's try to fill in our information. Looking at our table, I know 0, my y-intercept, is going to occur at negative 8. I know I'm multiplying by 2 every time. So if I were to go down to like 1, I know I'd be at negative 16. I can do backwards division to figure out what my other terms are. So if I do negative 8 divided by 2, this is negative 4. Divided by 2 is negative 2. Divided by 2 is negative 1. So if I look, all my terms are still negative. So I'm still going to be below my x-axis the entire time. So start at 0, negative 8. I know negative 1, 16 is way off the map. Negative 1, 4 is here. Negative 2, and then negative 3. So here is my function. Now the question is this an exponential growth or an exponential decay for this function as I shoot down very rapidly? This is still actually an example of exponential growth. Even though we are going into the negatives, we are still growing. We're growing and growing and growing negatively. Our values are getting larger and larger if we think about them all being in terms of negatives. So this is an example of exponential growth. So it's one way to determine between the difference between exponential growth and exponential decay. Growth occurs when our b value is greater than 1, or the absolute value is greater than 1. Meaning it could be positive 1, or it could be a positive value or a negative value. So as long as b is greater than or less than 1 or negative 1, then we are having growth. Decay occurs when we have a decimal or a fraction, when we have a value that's less than 1. So b is less than 1. The absolute value of b is less than 1. So if the positive or negative is less than 1 or negative 1, then, so if we have like 0.5, 0.75, 1 over 4, those are all values that are less than 1. That's when we're going to get a decay, when we're getting closer and closer towards that asymptote. But we're getting farther and farther away from the asymptote. That means we have a growth. Our y-intercept, once again, is 0, 8 for this, is 0, negative 8. Our asymptote is still y equals 0. As we look, we're still running up to that x-axis. We're still not getting anywhere near it, or we're still not getting closer, closer, closer towards it. So y equals 0 is still our asymptote. Our domain, I can still go in both directions. I can still keep going, and I can still keep going down. So our domain is still all real numbers, but my range is different this time, because rather than going all the way up to positive infinity, I'm going all the way down towards negative infinity. So the highest y value my function is ever going to get is 0. So 0 is actually going to be the top of our range, and negative infinity is going to be the bottom of our range. So we are actually getting y is less than 0. We're looking for all the values where y is lower than 0 or smaller than 0. That's going to be our range. All right, we're going to look at one last example, and then we'll call it a day. All right, so y equals 4 times 2 to the x minus 1. So this one is different. There's something added on to this function. We have that negative 1 or minus 1 at the end of our function. Let's see, how does minus 1 change our function? Let's pretend we didn't have negative 1. Let's create this table and pretend we didn't have negative 1. So if we didn't have negative 1, I know my function would start at 4. I'd be multiplied by 2, so I'd go to 8. If I'm going backwards, it would be 2, 1, and 0.5. So this would be if my function if it was just 4 times 2 to the x. But now when we have that minus 1, how does that change our function in there? What happens when we include that negative 1? Well, I'm just essentially decreasing one value from each of my y values. My y is just decreasing lower by 1. So 0.5 would be, minus 1 would be negative 0.5. 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 1 is 3. 8 minus 1 is 7. So all my values just decreased by 1. So if I look at my function, if I look at my graph, negative 3, negative 0.5 is right here. Negative 1, 2, or sorry, negative 2, 1 is here. Negative 1, 2 goes right here. Oh, sorry. I'm looking at the wrong numbers. Okay. There we go. Okay. So negative 2, 0 is right here. Negative 1, 1, because I need to look at my black and my green. Negative 1, 1 goes right here. 0, 3, and then 1, 7. So if I look, my function just 1 lower than what it should have been. In order to graph these functions where we had that this shift on this like a vertical shift on the bottom of our function, this extra number that's either adding or subtracting from our function, we are just shifting our function up or down on our graph. So by minusing 1, I'm shifting every point down 1. So my entire graph just shifted down 1. If I had like plus 7, I would shift everything up 7 spaces. So whenever we're trying to create a table for this, create the normal table and then create the shift on that table. So create that table and then change it at the end for those shifted values. So let's see how this affects. Well, based off the shape of our graph, it's still looking like it's a growth. Our rate is still greater than 1, so 2 is greater than 1, so we know it's a growth. Our y-intercept is now, instead of occurring at that 4, it's actually 4 minus 1, which is 3, so it's actually 0, 3. Our asymptote was y equals 0, but now that we shifted down, it's y equals 0 minus 1, which is y equals negative 1. We're getting super, super close to negative 1, but never actually touching it with our function. Our domain is still the same. We're still going all the way from negative infinity to positive infinity, so we're still all real numbers, and as a function, it should be. If we don't have a function, if our function isn't all real numbers, then it's probably not a function. And our range, let's look, it used to be we would get super, super close to that asymptote, or it's always super, super close to that asymptote. So in this case, our asymptote is now negative 1. So the lowest value our function can go is negative 1. So negative 1 is less than y, which is then less than infinity. You don't have to have the less than infinity part if you want it to. But as long as our function is greater than negative 1, then we're good. So adding this vertical shift on the end is going to just shift your graph up or down. You can sort of, like if you created this on Desmos, you would be able to put a slider here and you'd be able to slide it up and down and see it increase or decrease. All right, last question. Which graph best represents f of x equals 2 times 5 to the x? So based off this information, we know 2 is our y-intercept and 5 is our rate. So which of these best represents 2 times 5 to the x? So there's a potential of this first one. Maybe the second one. Is there a potential of this one? Well, looking at our y-intercept has to be at 2. Is this y-intercept at 2? No. Is this y-intercept at 2? No. So let's try to look between these two. So let's create a quick, so we know we're multiplying by 5 every time. So let's create a quick table. If we know we're starting at 0, what are our values going to be? So we know 0, 2 is our y-intercept. And we multiply by 5, we're going to go up to 10, and then we're going to go up to 50. So which of these show 10 and 50? Well, if at 1, I'm at 10. At 2, I'm at 50, so this one works. This one, at 1, I'm at 5. And at 2, I'm only at 25. So this one is not the correct rate. So we know our correct answer is this first one for our function. You could also plug it into Desmos and use that to help you as well. That's where we're going to stop it for today with graphing exponential functions. Using Desmos is probably going to be an easy way to help you visualize these when you work on the practice. If you have any questions over that, let me know. But have a great rest of your day.